Hi, in this topic we are going to see about TE waves and TM waves. So what do you relate from these diagrams? So EM waves are classified based on the type of field present and in the direction of wave propagations. We classified the EM waves into two types. First one is TE waves and second one is TM waves. So TE waves, in this Ez equal to 0. If Ez equal to 0 and Hz not equal to 0, Ey and Hx are exists. So Ey equal to j omega mu by h square dou hz by dou x, and Hx equal to minus gamma by h square dou hz by dou x. The wave equation is simplified to dou square Ey by dou x square plus dou square Ey by dou z square equal to minus omega square mu Ey, and dou square by dou z equal to gamma. First, the first equation becomes dou square Ey by dou x square plus gamma square Ey, which is equal to minus omega square mu epsilon Ey. By equating these equations and simplifying, we get dou square Ey by dou x square plus h square Ey equal to 0. Since Ey equal to Ey naught E minus e power minus gamma z, the above equations becomes dou square Ey naught by dou x square plus h square Ey naught equal to 0. The second equation is a differential equation and the solution is Ey naught equal to C1 sin hx plus C2 cos hx, where C1, C2 are arbitrary constants. Showing the variation in z direction, Ey equal to Ey naught E minus gamma z, which is equal to C1 sin hx plus C2 cos hx e power minus gamma z. C1 and C2 determined from boundary conditions. The boundary conditions are Ey equal to 0 at x equal to 0 and Ey equal to 0 at x equal to a. Applying boundary condition 1, Ey equal to 0 at x equal to a, Ey equal to C1 sin 0 plus C2 cos 0, which is equal to Ey equal to C2. C2 must be 0 to make Ey equal to 0 at x equal to 0. Therefore, the third equation becomes Ey naught equal to C1 sin hx. Activity. Applying boundary condition 2, Ey equal to 0 at x equal to 0, the equation Ey naught equal to C1 sin hx becomes, to make Ey equal to 0, h must be equal to m pi by a. Substituting the value of m pi by a in equation 4, we get Ey naught equal to C1 sin h m pi by a. Therefore, Ey equal to C1 sin h m pi by a x e power minus gamma z. Other field determinations are derived and finding hx equal to minus gamma by j omega mu C1 sin of m pi by a x e power minus gamma z, and hz equal to minus m pi by j omega mu a C1 cos m pi by a x e power minus gamma z. The dominant mode TEM0 wave or mode. In equation 5, 6 and 7, each value of m specifies a particular field configuration or mode. The associate wave is known as TEM0 wave or TEM0 mode. Hz value is fine. Then TM waves. For TM waves, Hz equal to 0. Therefore, Hx and Hy equal to 0 in the basic field equation. Ez, Ex and Hy will have values. So Hy equal to C3 sin Hx plus C4 cos Hx. The boundary condition cannot be applied directly to Hy to evaluate C3 and C4. Because H tan is not equal to 0 at the perfect conductor surface. Therefore, Ez is obtained in terms of Hy and then the boundary condition is applied to Ez. After applying the boundary conditions, we get C3 equal to 0 and H equal to m pi by A. The Ez, Hy and Ex values for Tm waves are calculated. Assessment questions. References. Thank you.